All right, this is section 11.2. This is on vectors. So 11.1, we discussed three-dimensional space and points. Points are basically used to build larger things like spheres. Spheres are collections of points, cones, things like this that we'll see later. Spheres we've seen already, but other objects we'll see later as well. But the other thing that we'll need to describe in this section is also, like in this course, is basically something like the movement of an object, or the position of an object, or the velocity of an object, things like that. And to do that, we'll need vectors. So what we'll do is we'll give the definition of vector, we'll give a bunch of examples, some comments about notation, and then a bunch of associated properties. So technically speaking, a vector, let's say in 3D, we'll sort of flip back and forth between 3D and 2D here. So vector in 3D is an ordered triple of real numbers. For example, 1, 3, 6. Now, in 2D, it's an ordered pair. So, for example, -5, 6. Now, at this point, you might look at this and say, like, well, this looks notation-wise exactly like a point. So, little however here. If I can spell that correctly. So the notation looks like a point. And what we'd like to do is change that, because we don't want to be getting these two things confused. And there are places where having the same notation will be confusing. So we need something different. So there are a couple of ways to do this, right? So option 1. So what I'll do is I'll draw like 3 or 4 options, and then I'll sort of get to the one that we're going to use. So option 1 is you could use something other than parentheses, right? So a classic notation is something like a bracket, like this. So when I say options, these aren't really options like that you can choose from. Like they're you know, you in theory you can use any notation you want. Like I'm not going to deduct points, but there's one notation that we're going to stick with. The same notation the book uses, the same notation that's classically used in Calc 3. But I just want to mention these so you're aware of them in case you've seen them in other courses. Second option, you could use like a horizontal bracket, like a square bracket. Option 3, you could do it vertically. This happens in like linear algebra. This is a pretty common notation. So option 4 is based upon the following fact. So before just giving it to you, I need to sort of tell you what it's based upon. So 2 facts. Fact A is vectors can be added or subtracted by adding or subtracting the corresponding components. Right? So vectors may be added or subtracted by adding or subtracting the components. In other words, the individual numbers. And B is let's say a constant, maybe multiplied by a vector. Or you could say this the other way around, a vector may be multiplied by a constant, but I'll write it this way, by multiplying by each component. So for example, if I took these 2 vectors, and I'll use parentheses notation for right now, because we haven't really officially got out of it. So 1, 2, -6, plus 3 times 0, 1, 5. So what A and B say, B says that second one, I can sort of distribute the 3 if you like. I can multiply by each of those. So 3 times 0, 3 times 1, 3 times 5. And point A says I can add those just by doing it component by component. So 1, 5, and 9. Now then what we'll do is we're going to define 3 special vectors. We're going to define the vector I. So this notation that has a little hat on it, we'll talk more about this later. This is read as I hat. It's like just like a little wedge shape. So I hat will be the vector 1, 0, 0. J hat will be 0, 1, 0. And K hat will be 0, 0, 1. So then, for example, the vector 1, 3, 6, the one we started with, this is the same as 1 times 1, 0, 0 plus 3 times 0, 1, 0 plus 6 times 0, 0, 1, which is the same as 1i plus 3j plus 6k. So this is the notation that we'll use. Again, it's not the only one, but this is the one that's classically used in Calc 3. All right, so you don't need to change this every single time, like in the sense that you don't need to write all the intermediate steps out. You could just say like, well, 1, 3, 6 is the same as 1i plus 3j plus 6k, and that's the notation. And then actually a couple notes I want to make about this, but let me clear the screen and make them on the next page. So some notes. In 2D, there's just no k. So for example, you might have a vector like, let me pull up these. So we have like a list of notes. So we might have like 4i plus 6j. Second note, you don't need a coefficient of 1. In other words, you don't need to write it. So for example, 1i plus 3j plus 2k is the same as writing it's the same as writing I plus 3j plus 2k. I will tend to habitually write the ones just to keep things neat and tidy, but you don't need to. The book doesn't. And you don't need to write zeros, like 0i, etc. So for example, if you had 2i plus 0j minus 7k, this is the same as 2i minus 7k. Again, I will typically write the zeros just because it's easier to make sure that I don't mess up, and lose track of what's what. But the book tends to not write the zeros either, so do as you want. And the last thing is the notation for vectors. In other words, to denote a vector, maybe the denotation. Use a letter with a line over it. So what I mean by that, for example, I could say the vector A is 2i plus 0j minus 7k. So there are some other options. You could write like a little arrow. You could write like a half arrow. Those are options. There are other things that come up here and there. Try not to just write an A. Right? Like the world won't end if you just write this, but you will get confused. Various places during the course we'll get to points where you have points and vectors combined, and if you have sort of bad notation, like for example, if I write something like CA, like with a bar over it, it's clear that I'm multiplying a scalar, like a regular number, times a vector, right? This is clearly number times scalar. But if you write something like CA, this, sorry, without the bar, right, this, you know, is A a vector or not? Like this looks like two numbers. Right? And so there are places in calculations, it's not just a question of keeping things straight, it's a question of calculations where this can genuinely be confusing. So please keep that in mind. Right? So next thing we want to look at is representations of vectors. Well, let's say representing vectors. Let's say visually even. So mostly I'm going to do this in 2 dimensions. We won't be drawing a lot of vectors, but knowing what they mean visually is important, as we'll see. And so typically the way it works is a vector can be thought of as an arrow that points in the direction according to its components. So let's say it can be represented by an arrow which points in a direction specified by its components. So if that's a bit unclear, that's okay. Let's look at an example. Oh, and before I give you an example, I'll say this. Where it's anchored, doesn't matter. And so, for example, the vector, say, A, which would be, say, 2i plus 3j. So we will draw that. The way that we can visualize that, we can draw an axis. And this is 2-dimensional, so it'll make it easy to draw. So what I'm going to draw is I'm going to draw an arrow which points 2 units in the x direction and 3 units in the y direction, to which you might say, like, well, okay, where do you anchor it? And the answer is, it doesn't really matter, right? So if I anchor it at the origin, right here, it'll go 2 over and 3 up. So it'll go right there. Or if I anchor it, say, right here, 2 units over, it'll still go 2 units over and 3 units up. So all of these are exactly the same vector. Put it right here. It'll go 2 units over and 3 units up. So right here. If you started, say, over here, okay, 2 units over and 3 units up. This is A, this is A, this is A, and this is A. These are all A, right? There's no anchor point specific, right? And again, just to see what's going on here, each goes 2 units in the x direction, because that's the 2i, and 3 units in the y direction. That's the 3j. So the I basically is telling you about the x, the j is telling you about the y, and the z is telling you about the k. Right? Now, just a little warning here, there will be times at which we will anchor the vector at certain locations. But in general, it doesn't have to be located anywhere, but often we'll anchor vectors specific locations for specific reasons. But we'll elaborate on that as we get there. For now, the thing to keep in mind that the vector is really a sense of direction. It's not a location per se. It can be anchored wherever, as long as it directionally it follows the components. So this is how we'll think about these things. So in 3 dimensions, of course, is much harder to draw. And like I said, we won't be drawing that many. Most of the ones we will draw will be 2-dimensional or abstract. So don't worry too much about those. So next thing I want to do is just talk about some basic properties of vectors and some associated definitions. Let me clear the screen off and do that. So associated definitions. So let me letter these out. So there's a term I used earlier, which some of you may know from physics, but a scalar. The term scalar is simply used to talk about things that are not vectors, like numbers which are not vectors. So it's just a different term. Is let's say a real number. All right, so for example, if I were to say 3a, the a is a vector. The 3 is a scalar. So second thing, vectors have a certain length, right? So the length, now there are two other, let me just say for now, the length of a vector a, which is say, for example, let me actually use a different letter than a, it'll keep things a little tidier. The length of a vector like v, which is ai plus bj plus ck. This is denoted by like a double absolute value. And equals square root of a squared plus b squared plus c squared. So literally, by Pythagorean theorem, is the length of the vector. If you draw it and you measure how long it is, it's this. And of course, in 2D, there's no k or no c. So you just omit that. And also, there are two other terms that are used for length. One is norm. The term norm is actually a deeper mathematical term that's used in other places. And magnitude, which is often used in physics. Length is sort of a nice word because we know it. It's familiar. Magnitude is generally used in physics. Norm is used in mathematics, but be careful because norm can mean other things. And generally, if you're working with different spaces, you have to know which norms you're talking about. But that's all right. So C. So a unit vector this is just a vector of length 1. So for example, the vector 1 over the square root of 2i plus 1 over the square root of 2j. This is because the magnitude of a is the square root of 1 over the square root of 2 squared plus 1 over the square root of 2 squared, which is the square root of a half plus a half, which is 1. So unit vectors are useful. We'll use them a lot. They're useful for giving a sense of direction where you want the length to be somewhat normalized and like made less relevant. So these are often used for pure direction, right, without a sense of length. And we'll see that as we go, but just so that we know. So D. So this is connected to C. So given a vector, let's say V, we have this phrase, the unit vector in the direction of V this is the vector V divided by the magnitude of V, or if you prefer, 1 over the magnitude of V times V. Now, just so you see what's going on here visually, if you have a vector like, let's say, 2i plus 3j, Actually, let's do a slightly better one. Let's do one that works out kind of nice. Let's do 3i plus 4j. This is definitely not length 1, right? This is pretty long, right? If you draw this vector, and if you say anchor it at the origin, let's actually give this the scale. If you anchor this at the origin, it'll be 3 units over, 4 units up. That is our A, our V, really. So if you take this thing and you divide it by its length, this is the square root of 3 squared plus 4 squared, which is the square root of 25. This is why I changed the values to make it nice, which is 5. So if I take 1 over 5 and I multiply it by V, remember this, I multiply 1/5 times both of the components. So 3/5 I plus 4/5 j. This is now a unit vector. And if you draw a picture of this, I need to draw a bigger scale here. There's my scale now. This vector is shrunk because you've divided both of those. You know, it was originally a length 5 and you multiplied it by 1/5, so you trimmed it down. So this is now about like this. This is now a unit vector. And so finding the unit vector in the direction of a given vector will also be useful later on as well. So it's good to know what this phrase means. So a couple of other definitions. Let me clear the screen off and do those. So E, the zero vector, let's see definition. This is denoted by 0 with a bar over it, and is 0i plus 0j plus 0k, or 0i plus 0j. You know, if you're in 2 dimensions, then you don't need to think about the k. And just so we're clear, it'll always be clear how many dimensions that we're in. So don't worry about which one the 0 vector represents. It's just all zeros, so no big deal. So second thing, or I guess second thing on this page, is one place the vectors will come up a lot, or they'll arise, is if you have 2 points. So given 2 points, like let's say P equals x1, let's say x1, y1, z1, and Q equals x2, y2, z2. We can construct a vector that points from P to Q. This is denoted by PQ with a line over it. You can also do PQ with like an arrow over it to say from P to Q. The book tends to use this notation, like with an arrow, right? But you can just do PQ, you know, to be unambiguous. And all you do, very easy, is you take the one you're going to, so from P to Q, let me underline this, and you subtract. So x2 minus x1 I, y2 minus y1 j, z2 minus z1 k. Now, it's pretty easy to see why you subtract these. So let me just show you an example. And I'll do it in 2 dimensions because it's easier to see. P equals 1, 2, and Q equals, say, 4, 8. And the vector from P to Q, I do 4 minus 1, I, plus 8 minus 2, j. That's 3i plus 6j. And if you draw this, it becomes immediately obvious why we have this. So our points, let's make those blue. Our points are 1, 2, and 4, 8. So clearly, if I want to get from 1, 2 to the point 48, I have to go 3 units over and 6 units up. So this is our PQ. Let me go back, let me mark those. That's our Q, that's our P. And just a little note here that PQ is not the same as QP. In fact, you can probably see now that QP is the negative of PQ, because you're turning everything around, so you're negating everything. But like I said, this vector will arise a lot, the vector going from something from one point to another point. So last definition. Then I want to talk a little bit about what vectors will represent for us. And then also comment about how they can be used with forces, but those can all be packaged together. So two vectors, let's say A and B, are parallel if they are non-zero scalar multiples of one another. I'm being a bit sloppy here. So when I say two vectors A and B, these vectors themselves have to be non-zero. So if this verbiage is a bit confusing, if they're non-zero scalar multiples of one another, look at an example. So say a vector like A is, say, 4i plus 6j plus 10k, and B is 2i plus 3j plus 5k. You immediately see that A is twice B. Right? A is 2 times B. So A is a scalar multiple of B, right? Or if you prefer, you can think of it the other way. Or is really the wrong word, it should be and. B is 1/2 A, right? They're scalar multiples, they're parallel. But for example, something like A is 1i plus 3j plus 10k, and B is, say, 5i plus 15j plus, say, 9k, doesn't work. Because to get B from A, you'd have to multiply 5 to get the i's right, 5 to get the j's right, but then it doesn't work with the k's, like they're not multiples like this. And graphically, they're parallel basically if they point in the same or opposite directions. Right? So I want to make that point about opposite directions. So visually, without any context, these vectors are parallel, like they're all parallel to one another. These are all parallel. Whereas, say, these two are not parallel to one another. So, last thing then is what will we use these to represent? So let me just sort of give you a couple of really simple examples. Let me clear the screen off, go through those. So uses of vectors, and most of these we'll see as we go. Like we don't need to go too far in depth about them, but we'll dig around a bit. So A, we will use these later to represent location. When we do this, we will anchor the vector at the origin. So remember I said it doesn't matter where you anchor it, but in certain situations we may anchor it somewhere specific for some specific reason. So for example, if I have like a red dot right here, right, then if I want to be like, look, a red dot, then what I can do is I can represent that using a vector. So if this is the vector A, then I could say like, hey, A is the position of the red dot. And that only makes sense if I anchor it at the origin. It doesn't make sense if I anchor it somewhere else. Now, the other place we can use it is to represent velocity. And in that case, we will anchor the vector on the object. So for example, if we're back to our red dot's up here, same location, let's say, but let's say it's going in a certain direction. Let's say it's going like up and to the left. This vector b, let's say v actually for velocity, then v could be thought of as the velocity. And it's not speed, like we'll deal with all this in more detail later, but speed is just a number, like 5 miles an hour, for example. Velocity in this case includes direction. This is velocity of the red dot. We'll also do this for acceleration, but you can see in this case it makes sense to attach it to the object. Right? And then the last place that we'll use this is to represent force. So in this case, we would anchor the vector on the object. Now this is not a physics course, so I don't want to dig too deep into units, things like that, but this can be a helpful place to sort of think about vectors. And so when we do this, in a case like this, adding, for example, adding vectors which represent forces gives resultant forces. If you're not a physicist and some of these terms don't make sense to you, that's okay. I'll give you an example. So something like might be the following. We might say an object at the origin, let's say, is acted on by two forces. One could be, say, F1. I'm going to make these vectors. They can be capital letters just so they don't look like functions. And they could be like 7i plus 1j. And F2 could be, say, negative 3i plus 2j. And we could say, what is the resultant force? So in other words, if both of these objects act, if both of these forces act on the object, like what is, if you combine these, what's the result? And the answer here is simply F1 plus F2. I'll draw a picture so we see. And this will be negative 4i, I'm just adding components, plus 3j. And so visually what's going on here that's a really crappy axis, that's right. We have these two forces. Let's make them red. So F1 is 7 units over, 1 units up. Remember the object is right here at the origin. Think of an object there. F2 is negative 3 and 2. So right here. So these two things are tugging on it. And when we add these, the result we get, which I'll do in blue, is negative 4 and 3. Hold on, I did not add those right. That should be a plus 4. Seems like I'm bad at math. 7 plus 3 is 4. Right there. 1 plus 2 is 3. So the result of these will be 4 units over and 3 units up. So 4 units over and 3 units up will be right there. So this can be thought of as the way that the object will actually go. So let me label that second force. This is F2. And then in blue, we have the resultant, this is the resultant force. So that's sort of how the object would actually go if these two forces tugged on it, because they sort of, the left and right kind of balance out a bit, and it gets pulled vertically. So, again, like all these uses we'll see as we go through the course. Don't obsess too much about them for right now. They'll come up as they come up, some a little later, some a little earlier. None of them really in this chapter. Well, the forces will. There are a couple of force problems in this particular chapter in the homework, but nothing to fret too much about. And then the location and the velocity, those will come up chapters 12, 13, and on from there. So don't panic too much about these. Just sort of get them in your head as uses of vectors. Now, the very last thing I want to do, just sort of a little appendix here, is just give a couple of pictures that can help us understand visually when we combine vectors what the pictures look like. And this isn't, these last couple of pictures are not something we'll use a whole heck of a lot, but we will use them. So they're good to sort of have these pictures in your head. So let me clear the screen, and then I'll just draw a few pictures so we can see those. Let me call this visual representation of vector operations. Sounds awfully fancy. Why are these so difficult? So, A, scalar multiplication. And I won't be too descriptive here. What I'll do instead, or for some of these, is I'll just give you a picture that helps you see. So, if I take a vector like, let's say I have a vector like this, A. I'm going to draw this without any axis, doesn't really matter. Then if I were to say make a vector like 2a, a vector 2a would just be twice as long. Right? So it would run right here. And if I did a vector like, say, let me do this in different color, like negative 3a, it would be in the opposite direction and 3 times as long as a. If I did like negative 1/2 a, then it would go in the opposite direction, be half as long as a. Let me do that one, and then probably we'll start running out of room. If I did like this vector, this would be negative 1/2 a right here. So that's a way to think about scalar multiplication. And we saw that when it came up when we did like a unit vector in the direction of something. So B, vector addition. So in the force resolution we saw this, but we didn't draw it specifically. But if you backtrack to that picture after you see this, you'll understand. So if I have a vector A and a vector B, we can get a good visual sense of where A plus B is as follows. If you draw a parallelogram using A and B, then A plus B turns out to be the vector that goes all the way across. And here I'm anchoring A and B at the same place in order to do this. So that is A plus B right here. So this lets you get a ballpark idea of whether you're right or wrong. You know, if you're adding vectors and you happen to have good pictures, you can look at the pictures and you'll know immediately possibly if things have gone haywire. And vector subtraction, this we won't really use. In fact, I can't think of a single place that we'll use it. But it's worth giving an example just to be complete. So we have like a vector AB. If we want to do A minus B, right? So what it does is it goes across the edge here. And then the way to think about which way it goes, because this is always a bit confusing, is like if you have, say, A minus B, and you add it to B, you get A. So what I'm going to do is I'm going to think of it that way. Right? So A plus B, this goes from tip of B to tip of A. Now, what I just said may be a bit confusing. Let me actually take a trip back to the previous one and point something out. This one back here, previous one, you can also think about this as just, you know, taking your A and taking your B and gluing it directly on the end. Right, if this is your A and this is your B, then your A plus B will just go like this. Same thing, you can see. So you can see that A plus B is literally like doing A and then doing B and spanning the entire difference. And so what you see in this third picture is that now we see that if you take B and if you add A minus B, the B's cancel and you get A. And that makes sense in the picture, because if you follow the B arrow and then you follow the A minus B arrow, you get the A arrow. And then, of course, last but not least, just to be completely complete, if you like, if we went the other way, right, if we did, like, here's B, here's A, if we did B minus A, we go like this. That goes from the tip of A to the tip of B. So like I said, these won't be used a whole heck of a lot. The first, let me do a couple of labeling. This one right here will be useful, but this is an easy one to keep in your head. This second one will be useful in a few places when we're drawing some pictures. This last one we'll almost never use. But I like to give it just because it gives a sense of completion, having covered everything. So that is the end of 11.2, and let me close up the video there.